So that's the first problem all worked out. Did you all understand why I made all the numbers negative? So remember that dx dt and dy dt, they're the rate of change, right? And if these two cars are heading towards one another, that means the values of x and y are decreasing. And remember to represent a function that is decreasing, or values that are decreasing. We do so by making the derivatives negative. Alright, so what else you guys got for me? Anybody actually look at the review sheet? I hope. Go ahead and pull that up while I'm waiting for you guys to decide what you want me to do. Can we go over one problem from each section of the review? As long as you keep telling me which problems to do, I'll do them. And we have time. So how about, for sure, I'll do the first problem, 1A, and then, let's see, what else do we want to do here? Let's do 2D. I know for sure you'll see those types of problems, so let's try that. Man, are you okay if I work on the board, or would you like me to just write on the paper and share my screen? What do you prefer? Anybody else want to weigh in? Okay. So let me go ahead and share the screen. Make sure that you guys can see it. I don't know why it's cut off. Give me a sec. See if I can stretch this out some. This is going all the way, but there we go. That's as big as I can make it. Alright. There's a little bit of the screen in the background, sorry about that. So let's make some space here. Or not. There we go. Alright, so the first one, if you plug into this one, you get, sorry, let's just plug in directly. So we get 2 squared minus 4 all over 2 minus 2. Well, that's 4 minus 4 all over 0, or 0 over 0. So, I taught you that when you get 0 over 0, that's an indicator you can use L'Hopital's rule. But we don't need to, right? We only want to use that if it's required. In this case, you could just factor. So if we look at the top here, we can do x minus 2, x plus 2. And then we can cancel these two. So this is now the limit. So x approaches 2 of x plus 2. Now we can direct substitute. And we get 4. So just because you get this does not mean you automatically got to go to L'Hopital's rule. Sometimes it's easier. Now the next one, you could do that. You could use L'Hopital's rule. But I want to do D down here instead. Actually, I think that one's factorable, but I want to use L'Hopital's rule on that one. Actually, let's do both on D, just so we can prove a point. Alright, so part D. If we plug in 3 directly, and you should always try that first, right? It's direct substitution is always the first thing you should try. And then if you get something strange, then you know you gotta do something else. So this is going to be 27 minus 27. And we're going to have 9 minus 12 plus 3. So we're going to get 0 over 0 again. So let's say this time I didn't recognize I could factor. So let's use L'Hopital's rule. So it says take the derivative of the top and the bottom. So we're going to get 6x up top. On the bottom we're going to get 2x, right? Minus 4. So we would substitute again. Looks like we get 9. Okay. So let's try it by factoring this time. So I see there's a 3 in common up there. And so that leaves me with x squared minus 9. And on the bottom, I'm looking for 2 numbers that multiply to 3 and add to negative 4. So it looks like x minus 3, x minus 1. And x squared minus 9 can be factored. As x minus 3, x plus 3. So on top I get 3 times One eraser. X plus 3 over x minus 1, because these cancel. And if I plug in, then this would be 3 times 3 plus 3 all over 3 minus 1. That's 3 times 6 over 2. Get 9 again. So that one's interesting because it can be done both ways. And my guess is you're going to say, oh, well, L'Hopital's rule was so much easier. Yeah, but sometimes the derivatives can be quite complex, right? Or if you had something like this x cubed up here, you could factor that pretty quickly if you had your formula. And the derivatives, you'd have to take 2 derivatives. So you'd have to use L'Hopital's rule twice. Or this one down here where it's x to the 4th and x to the 5th, right? That could get quite ugly. Good with those. So I'm not going to make you do anything about where is a function continuous specifically, but you should be able to find the domain of a function. Let's see. Find derivative of each. Let's do maybe B. G looks fun. Which one is that? Can you do 5C? I could, but I don't believe I'm going to make you use any hyperbolic trig functions, but I can still do that one if you really want me to. I think I'm going to do this one. And we'll figure it out from there. Should probably do some integration as well, because I guess you're probably still not very strong with those. So let's do some of these derivatives real quick. Come on. Alright. So if I want the derivative of this function, because it is a quotient, I need low times derivative of high, which is going to be cosine minus e to the x. So that's low d high minus, and I'm going to need more room here. Let me start over here. And then minus high times d low all over low squared. Okay. The ones I highlighted in red are ones that I'm wanting to do, that I think might be beneficial to look at. All right. So then let's see if there's any simplification we can do. We've got, if we multiply out, this is going to be cosine x minus e to the x minus x cosine x plus x e to the x. And over here we're going to get plus sine x, and then finally minus e to the x. So I'm not sure what the best way to write that is. I'm going to write it as 1 minus x cosine x plus x minus 2 e to the x plus sine x all over this. So unfortunately none of that's going to simplify down for us. All right. So somebody asked me if I could do C, so let's look at that one. So this one probably just looks weird because of the hyperbolic functions. The derivative of y with respect to x here. So derivative of the hyperbolic cosine is just the hyperbolic sine. And the second one, derivative of log, right, we get 1 over the inside. And derivative of hyperbolic sine is the cosine. And this, if you really wanted to, you could make it sine, or the hyperbolic sine, plus hyperbolic cotangent. I wouldn't worry about that one too much. Like I said, I don't plan on really giving you hyperbolic functions. Alright, so I wanted to do G because that requires some differentiation using the log, the natural log, or logarithmic differentiation. So the first thing you would do is take the log of both sides, natural log specifically. And that allows us to bring this cosine down in front. And then we take the derivative of both sides. So we take derivative with respect to x of the natural log of y. And we take the derivative with respect to x of this side. And so the derivative of natural log of y, well, that's y prime over y, because the derivative of natural log is 1 over y, and the derivative of y with respect to x is y prime. So now we need to take the derivative of the right-hand side. That's a product. So take derivatives of cosine, and you would get minus the sine, and leave the natural log alone. And then you would leave the cosine alone, take the derivative of natural log, which is 1 over the inside, which is x in this case. And then you multiply that y to the other side. So y prime is y times all this stuff. And if you know your basic derivatives pretty well, these problems aren't so bad. You just plug y back in, which is the original equation. So that's x cosine x times negative sine x log x plus cosine x over x. And that would be your answer for that one. So any other ones that you guys would like to see specifically? D is another one that's good for logarithmic differentiation. So is F. Y, you could do the same thing. Or for, sorry, H here, this Y equals. I did say I wanted to do this implicit one. So I'll go ahead and do that one, but while I'm doing that, can you please let me know if there's any other problems that you want me to do specifically. As if my computer lets me here. cursor's stuck. Uh-oh. Come on. Alright, so just like the log of y, we have to do this equation here implicitly as well. So we would take the derivative of sine. Derivative of sine is cosine. We leave the inside alone. And we're going to multiply that by the derivative of the inside because that's a chain rule. So derivative of x is 1, leaving behind the y. And derivative of y is going to be 1y prime, leaving behind the x. And on the other side, we're going to have the derivative of 2x, which is just 2. So then we just need to solve this for y prime. So y plus x y prime is 2 over cosine xy. Xy prime equals 2 over this minus y. I'm actually going to write the divide by cosine as secant. And then finally y prime is this. Okay. Alright, so number 9 was requested. Let's start there. Find the max and min value, any specific part of 9. I'd rather just do one rather than both. And while you're answering that, did I put the solutions on here? Yeah. Cool. I think the solution for 8b looks a little off there. Alright, so have you decided which part of 9 you want me to do? I guess if you don't give me one, I'll just pick one. Alright, so find max and min values. So max and min, that just means we need to use the first derivative test. Let's go ahead and do B, because I'm going to guess that's the one that probably gave you trouble. So we got to take the first derivative. And so that's going to be 1 minus 2 times, actually going to be plus sine x now. Alright, because derivative cosine is minus the sine. And so that's our first derivative. We need to set it to 0. And so we get sine of x is equal to minus 1/2. So for what values of x does that occur? So we got to do the inverse sine of negative 1/2, where you can use your unit circle. And make sure we're in the right mode. So let's throw this into degree mode so it looks like something we recognize. It says negative 30 degrees. Or that'd be what? I guess that does work because it goes from minus pi to pi here. So let's see. So that's minus pi over 6. And any other ones? So pi over 6 and 5 pi over 6. They're both positive, and then negative pi over 6, and what's going to be the other one? Seven pi over 6 works. Anything else? So the other value should be negative pi over 6 and negative 5 pi over 6 are your critical values. So then you would do a number line. And you would test to see what happens outside of those points. So you could plug in negative pi because it's equal to. So if you plug in negative pi, the sine portion goes to 0 and you get back a positive 1. So here it's positive. In between negative 5 pi and negative pi, we could do negative 4 pi, right? Or 3 pi, whatever you want. So if I plug in negative 3 pi over 6, the sine portion is negative 1. So f prime of negative 3 pi over 6, or just pi over 2, negative pi over 2, is going to be 1 plus 2 times a negative 1. So that's going to be a negative, right? So it's negative in there. And then we need something that's on this side, so we could just use 0. Sine of 0 is 0, and you get back a positive. So we do have two sign changes. So there's a maximum, right? If we're going from increasing to decreasing, then that means we have a maximum. So this is max. And if we're going from decreasing to increasing, that means we have a min. And since I have it open, we can plot that. So plot x minus 2 cosine of x respect to x. Okay. So this should be minus 5 pi over 6 here. That should be minus pi over 6. And this is a local max. This is a local min. Looks good. Everybody good with that one? Alright, so I know that you requested 12. Alright, so we can do that one. Let's find a point on the line that is closest to negative 3, 1. That is a optimization problem, specifically one for the distance formula, which we should recall looks like this. But recall that we can maximize instead the square. So I have the points, or I have a point negative 3, 1. I can plug or solve this second equation here for y. This is 9 minus 6x. So now if I plug into the distance formula, or this d squared part, doesn't matter which one you use as x1 and x2. I think I'm going to let the line be the first one. So 9 minus 6x is x, or sorry, that's y. I want x first, so x is just x in that case. And then minus the second value of x, which is going to be minus a negative, or plus 3. And then plus, now I want to do y2, that is 9 minus 6x, minus 1, quantity squared. And then if I'm doing optimization, I don't care about d squared, I care about the derivative of that quantity with respect to x. So you could square this whole thing out if you really wanted to. I think I'm going to go ahead and use chain rule. We'll get some practice with that. So if I take the derivative here, I'm going to get 2 times x plus 3 to the first, and then the derivative of the inside is just 1. And this second term here, I would get 2 times 8 minus 6x times a negative 6. So I've got 2x plus 6. Oops. Not sure why that moved down with it. 2x plus 6. And then over here we're going to have negative 12. So that would be negative 96. And plus 72x. So, looks like 74x minus 90. And if we're optimizing, we want it to be 0. So it looks like that's the value of x. And then you would take that number and plug it back into this equation right here to get y. So let's just calculate that. So you would just report your answer as an ordered pair. Like so. And I think we did 2 of those during class time. So you should have those in your notes to go back and look at as well if you want to. Or they should be recorded on the channel. Why are you moving? There. Alright, so 2 of you requested 13, so let me go ahead and do that one. So it says a farmer wishes to fence an area of 1.5 acres in a rectangular field, then divide it in half with, looks like it says that twice, with a fence parallel to the length shown below. Find the smallest perimeter possible. So another optimization problem. We just have to define the picture here with x's and y's or whatever you want to call them. So I'm going to call this length x, and I'm going to call this length y. So we want the smallest perimeter, so we need an equation for the perimeter. The perimeter is going to be 3 of these y's plus 4 x's. And then we're given the area here. that's the total area. So that would be this distance times this distance. So the area, which is 1.5, is equal to y times 2x. So you would then solve this equation for one of the variables and substitute it into the perimeter. So I'm going to solve for, I don't know, I guess y. So y equals, I would do 1.5, which is really 3/2, divided by 2x. So that's going to be what? 3/4x? So then plug that in here. So perimeter now equals 3 times 3/4x plus 4x, or 9/4x plus 4x. Oops. Turn it. So now we need to find p prime and set it to 0 in order to optimize. So the derivative of this function right here is going to be, so this is 9/4, and that's derivative of 1/x is going to become minus 1/x squared. And the derivative of 4x is just plus 4. Move the 4 over to the other side. Then swap out the x squared with the -4. So we get x equal 3/4. And if you have x, then you can find y by using this equation. So y equals 3/4 times 3/4. This looks like 1. Guys good with that one? Now, if the problem said specifically find the smallest perimeter, so we actually need to go back and plug these into the perimeter, right? We actually need P, which is 3 times 1 plus 4 times 3/4. So P equals 3 plus 3, or 6, it looks like. So I'm going to do this one, and I will do this one. And if you don't ask me any other questions, then that's all I'm going to do. So perimeter is not just the outer distance. Perimeter, when you've set up fence in the middle, is the total amount of fence used. So yeah, perimeter, when you have, basic shape, is just the outer distance. But if I have a rectangle that I cut into two, well, now I have to place fence there, so I have to add up all of those sides. We could do 14, but I don't think I said anything about making you guys do that on the final, so. Said 18D and 19E. Okay. All right. So this says find the derivative of the given function. So I want to find g prime. So remember that says, okay, if I have some function of x, I need to plug it in for t. So this would be sine of the cosine of x. But then I also need to multiply by the derivative of cosine, which is minus sine. So the one on the quiz, I put up the solution for you, so you guys should go look at that. I think it was something like 1 over 1 plus t squared, and I think the bound was tangent. So for that one, it would have been 1 over 1 plus tan squared, and the derivative of tan squared is secant squared. And 1 plus tan squared is also equal to secant squared. So the whole thing just equaled 1. That's what I wanted you to get out of it, but it didn't appear to come out that way. Alright, so D here. Evaluate each definite integral using the fundamental theorem of calculus. So that just means, right, that the integral of some function gives you back the antiderivative. So for D, the integral of dx over x is natural log. So this is natural log of x evaluated from 1 to 3. So natural log 3 minus natural log 1, and that's just 0. So you should just get natural log 3 out of that. All right. E here, so this is integral. I'm going to break it up. So this is dx over 1 plus x squared minus the integral 3x to the 4th dx minus the integral of pi dx. And one question I get a lot is, will I take off points if you don't write dx? And I absolutely will. So make sure you put it every single time. Just like if you don't put plus c when it's indefinite, like this problem here, that's points taken away as well. Right, so the biggest difference between when you have bounds, you plug them in, and there is no plus c. If you do not have bounds, then you should have a plus c. And you should know the difference between those two. Alright, so the second two are really easy. This one right here, that 3 doesn't really matter. We could just pull it out in front. And then x to the 4th, we add 1 to the power, divide by the number. And then this second one, or the third one, that pi can be thrown out in front. And hopefully you remember the integral of dx is just x. I'm going to go ahead and slap on my plus c so I don't forget it. The only one that's tricky is this 1 plus x squared. And if I remember correctly off the top of my head, I want to say that's inverse tangent. And that's probably the only reason that you were confused on the problem, because you didn't have that little cheat sheet in front of you. To remind you of that fact. Alright, so I think that was all the problems you requested. I did say I wanted to do this one quickly, so I'll do that. And if you have anything else, let me know real quick. So this one here I wanted to do because it is a u substitution. And so you would need to let u equal everything in the denominator. Du is the derivative of that times dx. which hopefully you see is the entire numerator. So this integral becomes du over u. I can change my bounds. So when x equals 0, u equals e to the 0 plus 2, or, whoops, 3. And when x equals 1, u is e to the 1 plus 2, or 2 plus e. Doing that makes it so that I don't have to change back. The integral of du over u is the natural log of the absolute value of u. And then I need to evaluate this from 3 to 2 plus e. So you plug in the 2 plus e first. Right, you always plug in the upper bound first. Subtract natural log of 3. And because that's two logs subtracted from one another, you could technically put them together and write it that way. I don't know why it's not letting me write. There we go. Alright, any other problems that you would like me to try or explain? Any concepts you just don't have a clue? Any more questions about the final? Will we see question 21? I don't think directly, but that doesn't mean that you wouldn't be asked to potentially use one of these properties. You don't have to use the properties when you do the integrals. They just make things easier sometimes. I mean, obviously b here, because it's from 1 to 1, right off the bat you say that's 0 and you don't actually do any integration. But the first one, a, from -1 to 1, you can use odd and even. 15, what was that? Somebody want to fill Shelby in while I look at 15, please? The Riemann sums. I don't think I'm going to have you do that. I'm more interested in the fact that you can actually integrate rather than add up a bunch of areas.